All right, statistics. We're on Unit 6, random variables. This lesson is on discrete and continuous random variables. Let's get started. So we know that a probability model describes outcomes of a chance process. And a random variable, so what we're defining, those take numerical values. And they describe the outcome of some chance process. So the probability distribution of a random variable gives its possible values and their probability of occurring. So we have discrete random variables. Now, discrete random variable, we define it as x. It takes a fixed set of possible values that have gaps. So like flipping a coin, rolling a dice. Now the probability distribution of a discrete random variable, x lists the values, xi, x sub I, and their probabilities, which would be p sub I. And here's like a table. So for the outcome x1, it has a probability of p sub 1. For the outcome x sub 2 has a probability of p sub 2, and so on. Okay. And the probabilities, they have to satisfy two requirements, and we've kind of already touched on this before. Each probability is between 0 and 1, and the sum of the probabilities has to add up to, yes, 1. We already know that. So here's our sample problem. Go ahead and take a moment and read it. And then they give us this table down below here. So you have 0 goals, 1 goal, so on, up to 9. Show that the probability distribution for x is legitimate. Are all of these probabilities between 0 and 1? Yes. So check mark. And then we're going to add all of these together. All of these, we add them up. Does that equal 1? They do equal 1, so we're good. It is a legitimate probability distribution. Next, what's the probability that the number of goals scored by a randomly selected team in a randomly selected game is at least 6? So they're asking at least 6. Well, 6 is our cutoff. We want this space here. So that's going to be the probability that x, which is our number of goals, is greater than or equal to 6, is going to be 0.041 plus 0.015 plus 0.004 plus 0.001. That's going to equal 0.061. So now we have the mean of a discrete random variable. We talked about this before. It's the expected value. So what do we generally what do we generally think is going to occur? That is an average of the possible outcomes. And each of the outcome is weighted, so it's a weighted average, and it's weighted by its probability. Okay. So definition, suppose x is a discrete random variable, and here's our probability distribution. So before it was hockey goals and the chances, right? To find the mean, the expected value of x, we multiply each value by its probability. Okay, then we add them all up. So E, capital E, is expected value of x. That's mu of x, and that's x1 times p1 plus x2 times p2 plus da 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 da. So we use our sigma notation where we have all our possible outcomes, and I equals 1 and to n, okay, whatever. But we don't really need to do that right now. I'm not going to worry about that too much. So, and if we interpret it, if we perform many, 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 many trials, we expect the average to be, and then this right here. And this goes along with our law of large numbers, right? As the samples get larger and larger, they should approach our population proportion of probability. So we use the mean. You can guess we're going to use the standard deviation as a measure of spread. Okay, it's the definition of variance of a random variable is similar to the definition for quantitative data. So suppose we have, here's a definition. Suppose we have x. Here's our table again, and that mu x is the mean of x. Remember, that was our expected value. The variance of x, our x, is going to be sigma squared of x. And here's how you find it. You find the first outcome minus the expected outcome, and then you square that, and then you multiply by that probability. So these two things are going together, okay? And you continue, and you sum this up, and here's your sigma notation for that. Then to get the standard deviation of a random variable, you take the square root. Oh my gosh, the cats. So then we have sigma, lowercase sigma x, and that's just the square root of the var. And this is the same stuff we had written above as our sigma notation. So interpret, when it says interpretation of standard deviation, you'll get questions like this. On average, the goals scored will differ from the mean of whatever the mean was by about sigma x, okay? And this is what it says. You'll get questions that say interpret. What was that? You'll get questions that say interpret the standard deviation in context. And you're going to say, on average, the goals scored from our hockey example will differ from the mean of mu x by about sigma x. But you will use numbers here because you will have calculated it. Speaking of calculating, here's our hockey example again, okay? So let's highlight the important information. 1,319 games played in the regular season. X equals the number of goals scored by a randomly selected team in a randomly selected game. Now, if you notice, these words are important to say. The table below gives the probability distribution. We know that it's legit because each one is between 0 and 1, and also they sum to 1. So all pi between 0 and 1, and the sum of the probabilities equals 1. We're good. Now it wants us to compute the mean and the standard deviation. Let's do this by hand. I will pause. So here we have the mu of x, which is the expected value of goals scored by one team, randomly selected team in a randomly selected game. And you have 0 goals times the probability that they score 0 goals, plus 1 goal times the probability they score 1 goal, and so on and so forth for each number of goals scored, all the way up to 9, which is at the end of our table. And when I do the arithmetic here, I get 2.851 goals scored. So what does that mean? When we look at many hockey games, we would expect a random team to score 2.851 goals per game on average. Put those in different colors so they stand out to you. Okay, it's important that we use these terms, expect, because we're looking at expected value, and they're asking what does this average mean in the context. And because we're using a very specific number, 2.851, we calculated it using the distribution. We are very explicit and say that it is on average. It is an average. Next up, standard deviation. So here I have sigma x, our standard deviation of x, and x is our number of goals scored in a random team in a random game by a random hockey team. So here I have 0 goals minus the expected number of goals, and then I square that, and I'm multiplying it times the probability that this is the difference. 0 is the difference from the mean. And then I add to that 1 goal scored minus the average number of goals scored. And I square that difference, and then I multiply it times the probability that my goals scored will differ by this amount. And I continue on. That's what this means verbally. And I left off a little exponent there now that I see it. When I do all this mathematics, all the maths here, I get 1.6324 goals. Okay, that's the standard deviation. What does this mean in context? Meaning, how do I explain this to someone using words? In context, on average, I highlighted that, the goals scored in a game will, highlighting here, vary from the mean of 2.851 by 1.6324 goals. This is the units we're looking at, goals. So units in context, we're still doing that, okay?